Okay, there you go. Hold on, I have to say got it. Yeah, so we're happy today to have Harley Scammell, who's at UNSW, and let's see. Oh wait, you spent time at Harvard. You got your PhD at UNSW, you spent time at Harvard, and I feel like I missed a spot, or did I not miss a spot?
No, that sounds right. Yeah.
Okay. Anyway, but he's in Fleet now, and he's going to talk about exciton, condensation, and Bilayer Graphing.
Okay. Thank you so much. Yeah. So this is work between myself and Oleg Sushkov on exciton condensation in Bilayer Graphing. But we benefit from lots and lots of group meeting discussions with Iden, Zeb, and Jack as well, who are also in the theory group of Oleg. So the roadmap for today is I'm going to discuss bilayer graphene, but the emphasis is on biased bilayer graphene. So just discuss the single particle properties, then excitonic bound states. And then they'll get a little bit, I guess, slightly technical in the Coulomb screening section, because this is really where the crux of the theory is. And then I'll discuss exciton condensation at the end, and phenomenological properties, and of course ask questions along the way. So bilayer graphene, or biased bilayer graphene, is sort of depicted here in this cartoon. By the way, do you see my cursor? This doesn't matter too much.
Yes, we can see it.
Thank you. So the two sheets here, these gray sheets are the two graphene layers of bilayer graphene. And important point is this is AB stacked bilayer graphene, so it's the most stable form. And on top of this, we've got metallic gates, these darker gray rectangles that are symmetrically placed a distance lowercase d above and below the bilayer graphene plane. And these impose a bias field. So there's some electric field here I've drawn vertically. Having the two gates means you can simultaneously control chemical potential and an effective band gap. So yeah, key point is that there is this bias field opens up a band gap in bilayer graphene. So I've drawn a schematic of the band structure. And normally without a bias field, bilayer graphene, this is everywhere in this talk, chemical potential is at 0, so it's at half filling. This would be a semi-metal, so these bands would be touching. But due to the bias field, we open up a band gap. And in the notation, this will be 2 delta. So it's delta above and delta below. The other key point, of course, in graphene systems is that you have 2 valleys, tau plus and tau minus. So what's been measured experimentally is that this bias field D is linearly proportional to the band gap. And this is true for a huge range of field. So we'll just take this as a given. This is in this experiment by Zhang. The minimal model that describes this band structure is given here. It's very, very simple. And this just describes the solid lines. I've also drawn in dashed lines, and these are extra bands at higher and lower energy, but they won't participate at all in the analysis. They're separated by an energy gap of about 0.4 eV, and we're not interested in energies of that scale. So you can capture this 2-band model with this 2x2 Hamiltonian. And this is at a given value, let's say tau plus. Key properties are that this bias field enters on the diagonal, and your kinetic terms are on the off diagonal. What you see from here is that what I'll call particle hole symmetry is that whenever you're at some given momentum in this upper band, in the conduction band, the valence band is exactly negative of this at the same momentum. Another point is that a low momentum expansion around this band minimum gives you a quartic dispersion. Okay, so they're just a couple of features of this minimal model of bilayer graphene. But this is a robust band structure, and a lot of all corrections are known. And so I gather these in delta H. So I want to point out that in delta H, you have, in red, this is a particle hole symmetry breaking term. It's most easily seen because this is proportional to high density matrix. So it means that instead of these 2 quartic dispersions, you now put in a quadratic dispersion, say both facing up. So it kind of, if you like, it affects the band mass differently in the conduction versus valence. So you don't have this nice relationship anymore. Also inside this bracket is this term that's proportional to delta over delta naught. This still respects that particle-hole symmetry, but it just introduces, instead of the bands being quartic, it would make the bands quadratic. So if you looked at Landau levels, this actually breaks this accidental orbital degeneracy that people might be familiar with. So this is also, this I gather this is a perturbation. And then the final term is the trigonal warping, is off diagonal. So if you put the chemical potential somewhere in the conduction or valence band, up until now, the Fermi surface was perfectly circular, but with these terms, you break this down to a threefold rotational symmetry. So it's trigonal. A key point is that all of these parameters, M, capital M, delta naught, and pi naught, are known. These values are fixed elsewhere. And they're probably fixed through DFT calculations, but also via direct experimental measurements and then fitting thereafter. So we'll take the values from Kuzmenko. There's probably some 5–10% deviation across different experiments. So taken together with this linear conversion between displacement field and band gap and all these parameters, this single particle Hamiltonian is completely fixed. We have no freedom in what we do. So it's really honest. So what I discussed today is exotonic bound states and then subsequent condensation. So just to quickly review the essentials is that we take this is some generic semiconductor, and this dashed line is the Fermi energy. So we have completely filled valence band, and then you kick an electron into the conduction band, and so you have a negative charge in conduction and a positive hole in the valence band. So these excitons form a bound state because there is then an attractive Coulomb interaction between the positive and negative charges. So in terms of energetics, of a single exciton, it has a total energy E. This is a zero total pair momentum of the exciton, which is given by how much energy it costs you to kick it across the band gap, minus how much the binding energy is, which is basically how much attraction between the positive and negative charges there are coming from Coulomb. The game we want to play is how can we get this capital E, the excitonic energy, to become zero and then negative. This implies that instead of it being a band insulator where you can somehow excite excitons above it, now the excitons would become the new ground state because the system becomes unstable and it would spontaneously rearrange. So this is what we're interested in. So it can be formulated in this very, very simple way. When does EB exceed the band gap? So just to pause here for a second, because you might be wondering, well, Coulomb is Coulomb. It's always attractive between a positive and negative charge. Why don't you just set 2 delta equal to 0? Because then you would have condensation. And this is kind of the logic that a lot of people use. I'm not putting any doubts on that logic. And this is essentially BCS theory as well, because you're starting a semi-metallic. Well, here, the 2 delta equals 0 is the semi-metallic states. You make these 2 bands touch. This would also hold if you created a Fermi surface of equal and opposite charges. And it's the same statement as BCS superconductivity, is that any arbitrarily weak attraction would give you a condensate. But we'll see by the end of the talk that actually, even though that seems mathematically like the simplest thing to do, it isn't the best way to have a stable condensate. So I'm going to quickly go through the quantum numbers of these are the individual excitons I'm talking about at the moment. What are the quantum numbers? Well, you have valley structure and you have spin structure. So for valleys, you can either pair electrons and holes in a given valley, or you can pair across valleys. And this has a physical difference because one would give you a total momentum of 0 and one gives you a total momentum of plus or minus 2k. K is the valley momentum. It's the high symmetry point. And in terms of just pure Coulomb, there's no distinction between these 2 pairing energies, but there is some slight difference in terms of form factors. This is a little technical detail, but at the moment we can just assume these 2 different states are degenerate. Spin, I'm going to pretty much not talk about spin at all, but there's something I think is quite interesting, is that, of course, when you have a 2-body problem and there's 4 possible combinations of spin, but it's most convenient to group them into spin singlet, which is anti-symmetric under exchange, and spin triplet, S equals 1, which is symmetric under exchange. And now for a normal Cooper pairing problem on a Fermi surface, singlet and triplet are necessarily not degenerate, unless there's an accidental degeneracy. But for excitons, because of this extra conduction and valence band, I guess it's a quantum number, the excitons, so the singlet and triplet are degenerate. So with that in mind, we can actually just completely ignore spin. But I think that was a curious point for me. Okay, so we want to go back to these individual excitons and look at their energetics. Now, the appropriate thing to do is to look at the two-body Schrodinger equation. So I just want to talk you through the ingredients. This is that same E we were discussing before. This is the conduction band and valence band. So this comes from this single particle Hamiltonian. Psi is the two-body wave function at relative momentum P. So total momentum is set to 0, or it's set to this high symmetry 2K, but these two cases are treated equally in equation 6, more or less. On the right-hand side, we have the Coulomb interaction, which is attractive, and also this form factor, which I want to keep it here for bookkeeping, but we can set in your mind this equals 1. So equation 6 is just the sort of the mechanics behind what's going on in this very simple equation that we're after. So you can see that this 2 delta comes from this single particle part, and then whatever's left over, which is predominantly Coulomb, gives you your binding energy. So large Coulomb equals large binding energy. It's a very obvious statement. So the question for us is, how large can we get this interaction?
Could I ask a question?
Yes, please.
As I recall, when the displacement field is quite large, you could have some kind of Mexican head dispersion.
Indeed, yeah.
In enhanced density of states.
Mm-hmm.
Would it be more favorable for the point of view of excitons?
In terms of density, actually, it's a little bit of a tricky question, yeah, because you enhance density of states. My understanding is that this Mexican hat affects upper band differently to lower band valence conduction. But this is captured in this delta H corrections to the single particle Hamiltonian. So
I see.
So I've got it, or it's already embedded in equation 6. I just don't have a very simple reasoning to be like, oh, more Mexican hat is better. Sorry, I don't have that analysis in my head. But this is already captured.
Okay, thank you.
No problem. Yeah, so the game is, how large can we get the Coulomb interaction, which is equivalent to saying how large can we get the binding energy in bilayer graphene. I mean, the Coulomb, like I said before, Coulomb's Coulomb, we get this from the universe, and it's in terms of fundamental constants. But then we jam it inside of a 2-dimensional material, and then we put things around this 2-dimensional material, and all these things that we do to Coulomb end up reducing it. So how do we not reduce Coulomb too much? So the first point is pretty obvious, is that there's dielectric screening. So we have Bilayer Graphing, and you can put a substrate or superstrate above and below. And this incurs a penalty of epsilon r. So this multiplicative, it's very simple to visualize. So for example, a typical experiment with experiments that I've seen are with HBN encapsulation. So then we lose a factor of 4 on the strength of Coulomb. Second point is gate screening. So what does gate screening do? Well, here we've got gates symmetrically above and below the bilayer graphene plane. And it incurs this penalty of hyperbolic tan Q times D, and D is this distance. So most of your dynamics are happening at small q. Q is this momentum transfer. So whereas previously this would be a diverging quantity, it's now cut off. There's some infrared cutoff effectively given by 1 over D. So, I mean, you can see from equation 8, what you want is a large distance, the gates to be well separated from the bilayer graphene plane. But how far is necessary? We'll see this by calculation. And by the way, gates are unavoidable because we want to apply a bias field, so we need gates. And the third, okay, I've been calling these handles, but this is, you don't really have much choice here, but this is RPA screening. So this is how Coulomb acts inside the two-dimensional plane of bilayer graphene, creating virtual particle hole excitations, which act to reduce the Coulomb interactions. This is the standard screening picture. Of course, sign convention is with us forever, but it's really annoying. So we have a minus sign here, but this object, this operator is negative. So the RPA screened interaction is lower than an interaction, the Coulomb interaction that didn't have to deal with creating these particle hole pairs inside bilayer graphene. So far, these are the only three things that happen to the Coulomb interaction in our scheme, and they're all bad. they all reduce Coulomb. But then there's something I should actually say on this slide. This is the standard way to treat Coulomb interaction. You always say, okay, I just want to take the static case. It's just, I mean, at least theoretically, because it's just easier to deal with. But then we asked ourselves, well, what goes on with retardation? So just pure mathematically, the polarization operator, if you evaluate this at a non-zero frequency, this is smaller than the polarization operator in the static limit. So this is a crazy way of saying it, but you could say that retardation is a source of anti-screening, meaning that the retarded potential is stronger than the static potential. Of course, this is, I've just juggled it in a strange way, but actually there is some physics behind this. But what this means is I'm saying that if you, say for the exciton problem, if you have an electron and a hole interacting instantaneously, the potential between them is weaker than if the electron and hole interact at a different time. That's what's going on here with retardation. This will kind of be our focus. So the full Coulomb interaction is actually this object, equation 10. And now, obviously we need to quantify how large this retardation is. If the difference between the retarded potential and the static potential is something like 10 to the minus 4, then who cares? But that's not the case. So let's quickly try and quantify in an easy way what goes on with retardation. So this is the polarization, this left-hand figure is the polarization operator. Remember, it's bad when it's its largest. So the static limit is this, you can probably barely see it, but it's the blue line, it's the largest line in blue. And then as I just put in different frequencies, I reduce the polarization. I reduce screening. And another way to sort of measure this might not actually be the best way to measure it, but we define this object chi screen, which is the full retarded potential divided by the completely bare potential, just to avoid any divergences. And the larger this object, the stronger the Coulomb attraction is. So we see that the static case is the weakest. And then as we go up in just these different frequencies that we put through the bubble, put through the polarization operator, we are increasing the attraction. But this kind of doesn't tell us the full story, because whatever we do, we probably have to integrate over this frequency, and maybe there's weight factors, and maybe in the end it's still 10 to the minus 4, the difference. So we actually have to do a calculation. But in any case, we can see that retardation could be significant. I mean, we're seeing factors of 2, 3 difference in screening properties. The problem is then that the Schrodinger equation is not appropriate, because you can't have a time dependence in the potential and use this Hamiltonian method. So instead you have to have the Bethe-Salpeter equation, which is equation 11. And this equation looks kind of fine, but it's really cumbersome and difficult to implement numerically. So what we're looking at here, this is essentially the exotonic Green's function, this chi it depends on frequency and momentum. And it's a self-consistent equation because it also appears on the right-hand side. Kind of looks a lot like BCS, but it's a little bit challenging. People probably have nice numerical routines for this, but we said, no, let's do something that we're more comfortable with, and let's do perturbation theory. And to our surprise, we haven't seen other people approach it like this. Maybe it exists, it just took a different name. But the idea is kind of the standard perturbative idea. We start from the static limit and perturb in the difference between retardation and static. So if you start in the static limit as your 0th order, okay, this is 0th order Green's function, contains this separable product of a Lorentzian that has all of your frequency dependence and a wave function which comes just from directly solving Schrodinger equation. So we get that for free. It's really cheap to compute. Let me just multiply this. And this E0 is the E0 from Schrodinger. And so we calculate the first order correction to energy, which you can see this is just sandwiching the change in the potential with respect to the original wave functions that here, they're Green's functions. And this is the object that we compute to sort of quantify how significant retardation is. You can check that in appropriate limits, this reduces to a quantum mechanical, the quantum mechanical result for a change in energy. So armed with this, we now come to basically the key result, and that is presented here. So first we have the static limit. And so this is the binding energy, superscript naught. And then we also include retardation, which is included in this perturbative way. So binding energy naught plus the correction to binding energy. So it's basically the minus of 13. And then there's 4 different cases here. This is where we place the metallic gates in nanometers, a distance d equals 20, 100, 300, and 1000. And everywhere the dielectric is 1. So we're considering suspended bilayer graphene. Comparison of left to right, you see that the binding energy, this capital E was supposed to be epsilon. We see that the binding energy with retardation is significantly larger in this currency. So retardation has a massive effect.
Sorry, Harley, can you just explain your currency again?
So here I just, sorry, this capital E is actually supposed to be epsilon B. So this is the binding energy. And we divide by the band, well, delta is half the band gap. So this is some dimensionless quantity. And the key point is that we were looking for the case when binding energy equals 2 delta. So in this currency, this is the condensation point where we've truncated the plot. So let's purely look at the right-hand side because this is more elaborate calculation. So
right.
when we're at large delta, let's just choose a particular curve. Let's choose red. When we're at larger delta, the binding energy is less than 2 times delta. So we're in the band insulator phase. And then as we go along and lower delta along this red curve, we're getting closer and closer to this transition point where this equals 2. And we see that when we place the gates only at 20 nanometers, okay, you can continue this point, maybe you strike 2, maybe you don't. We're getting closer to this condensation, but for d equals 100, we certainly hit condensation. So the key points are that retardation has a huge effect and that gates have a huge effect, especially when there's some sort of transition between d equals 20 and 100. Beyond 100, it's becoming less and less significant.
Could I interrupt you?
Please.
Could you, I have missed it. So if you have a gate, it could not only open a gap, but also could induce charge carriers. So it also could.
You can induce charge. That's right. So they use a double gate system. So this allows them to simultaneously fix their chemical potential at inside the band gap at half filling, as well as opening the band gap. I think if you just have a single gate, then you're in a lot of trouble because you can't, you don't have this manipulation. Yeah.
Okay, thank you.
No problem. Well, I need to move this. Sorry. Okay. Right. So yeah, key point retardation is crucial, and you want to place the gates some distance 100 nanometers or more away. But what's a little bit curious is that, okay, take as an example point that delta equals 30 MeV. You can calculate the characteristic radius of an exciton, and you find that it's about 10 nanometers. And then it's a bit strange that if an exciton is only 10 nanometers and then the gates are 20 nanometers above and below the plane, then why should it matter so much that you 20 versus 100? And we don't have I guess, an analytic argument for this other than that the tail of the wave function matters in real space. Because these axes are a little bit funny, I've given this schematic of the phase diagram. So here, order, you can replace this with, let's say, order parameter or temperature. Let's just call it temperature. So what we've looked at so far is starting in the band insulator phase and then driving, which is where individual excitons cost more energy, positive energy to excite. And then we've driven down along this zero temperature axis and realized this quantum critical point, where we can enter the phase, enter the condensate phase. And implicitly in everything I've said, I've been sort of suggesting that doing it this way, as opposed to somehow starting in the condensate and trying to calculate properties of the condensate, is a much more accurate way to go about things, because you just have this two-body problem versus a many-body problem. I just want to spend 3 slides verifying that this is true, that if we have the two-body problem, we have highly accurate techniques. So what do we have at our disposal? There is data for uncondensed excitons, so deep in this phase over here in the band insulator, for HPN encapsulation, so this dielectric of 4, and D equals 20 nanometers. Sorry, I didn't link what experimental paper this was, but there's two key observations that we can compare our theory with, and that's the binding energy versus delta, or the total excitonic energy versus delta. And this occurs with both S-wave excitons and P-wave excitons. This is what they're able to excite. They also have this Zeeman splitting of S-wave excitons with a G factor of 19. So this is, I said this is puzzling, because I mean, if it was spin, then G factor should be somewhere on the order of 2. So really there's some orbital contribution, but it's S-wave. So just to confirm, these are certainly uncondensed excitons, because D equals 20, that was already like under the critical, the sort of minimal distance you can choose for the gates. But on top of that, there was epsilon equals 4. So you're certainly not in the condensate phase. So computing the exciton energy, this is not binding energy, this is exciton total energy. Okay, let me say, so the S-wave, the experiment is the points, and the black circles are for the S-wave exciton, and the gray squares are for the P-wave exciton. And then there's 2 fits per set of data. The dashed lines are when you just use the minimal model, so you don't include things like this Mexican hat or particle Hall symmetry breaking, trigonal warping, anything like this. And the solid lines are when you include all this delta H, all these additional factors. So it becomes sort of irrelevant at smaller delta, but there's some more deviations at large delta. And that's because one of the terms in that delta H Hamiltonian was proportional to delta. But this is excellent because Hamiltonian was fixed by other people. We had no fitting parameters, and the Coulomb attraction is completely fixed because we know what epsilon r is and we know that D equals 20. So we had no fitting parameters, and this is what we get. So that's kind of absolutely crazy. In my world, that's totally crazy because you usually have at least one fitting parameter to make things work. So two-body techniques are looking good so far. Now there's this puzzle of Zeeman splitting. And there's a delicate issue because of valleys and as well because there's positive and negative charges. But let me just say that what I'm calling S-wave in this previous slide, these black points, are L equals 0, but this is in quasi-momentum. This is the L of a given valley. So on top of this, you have to worry about valley quantum numbers. So in experiment, they're only probing this P equals 0 state because they excite via photons. So what's going to happen is actually this splitting is going to be a splitting between the exciton in valley plus and exciton in valley minus. So let's have a quick look at the issues here. So here's a cartoon, and this is like a classical picture that this is the excitonic bound state. We have electron and hole with opposite charges. They rotate together. Well, they've got the same angular momentum L under the same B field, a magnetic field, but they have opposite charge. So when you sum these Zeeman contributions, say from orbital dynamics, if they have the same effective mass, basically if it's a particle hole symmetric band insulator, then the orbital contribution is 0. So this is also a good way to measure what the particle hole symmetry breaking is. So in equation 14, Z just means I extract the Zeeman part. This was just for orbital, but now I include what goes on with valleys. It's a really subtle, it's a pretty subtle calculation, but extend this same sort of logic. And I put in here in this quotation, particle hole breaking terms. And I said there was only one particle hole breaking term in this Hamiltonian delta H. So we immediately see that our theory, okay, this theory will tell you that the G factor in appropriate units is just proportional to 2 over m. This is that same red m I had in delta H. And you just put in those same numbers, which we also weren't fitting parameters, and you get 18, and 18 obviously equals 19. So basically these two-body techniques are excellent. So we're really confident in what we're saying. So now I just want to talk about some of the phenomenological properties of the condensate. And in this part, actually TC versus delta, we can still use this same two-body approach because this is always at the critical point. So we're happy with how reliable our calculation is. But then when we consider actual properties of the condensate, we have to rely on sort of uncontrolled many-body techniques. So it's more qualitative in nature. But I just want to raise these 3 points. So at the start, so here's the critical temperature at 2 different versus delta at 2 different values of the distance to the gates. And at the start of the talk, I said, well, why don't you just set 2 delta equals 0? And then you're immediately in the condensate phase. Well, when you set 2 delta equal to 0, you also enhance screening significantly because now you're in a semi-metallic phase. And in the end, how this looks when you do the full calculation is that you kill TC. Okay, we don't have the calculation explicitly at delta equals 0, but basically you go to something that could potentially be well below a Kelvin. And I believe this is what goes on when people consider exciton condensations out of a semi-metallic state. But I can't make that semi because I only have calculations for bilayer graphene. So key point is that this band gap or this bias field delta is providing an excellent handle to tune to find a maximally stable excitonic condensate. And these critical temperatures are pretty big. And we're careful with this calculation too. We take into account Pauli factors, or Fermi factors for the excitonic legs, like people would do in a BCS theory. But we also take into account the finite temperature corrections to the polarization operator, which I rarely see people do in BCS theory. Well, yeah, in BCS like gap equations. And those two effects contribute approximately equally, probably the screening more so. But, oh yeah, this was the same question. If you're convinced by these plots, then I've answered this question. Why would you set delta? Why not just set delta equal to 0? Well, your critical temperature also is tending towards 0. The problem is that the excitonic condensate is a neutral superfluid. So it's not easy to directly probe into a transport measurement. So here we're trying to propose how actually to look for it. And so what do we have at our disposal is that this displacement field acts on these bilayer graphene to create a polarization, so a sort of dipole layer between the 2 layers. So considering just the band insulator regime, you can see that, okay, chemical potential 0, so we completely fill the valence band. And you can see from the Hamiltonian that if you put this to the top of this valence band, you put momentum equals 0. This is a purely diagonal Hamiltonian. And this is in the basis of A1 and B2, meaning layer 1, layer 2. So this point here is sitting purely on layer 2, meaning you're completely filling layer 2 when you add this polarization, this bias field, which is a pretty obvious statement. You put a field, charges also move towards it. negative charges move towards it. Of course, when you include higher momentum, there's a little bit more mixing between A1 and B2. So in the end, you have to sum up appropriate quantity, but you see that there's some large polarization. Now, if you kick out an electron from the valence band up into the conduction band, leaving behind a hole, then you start to put a negative charge upstairs and positive charge downstairs. So this is working against this net polarization, this net dipole moment. Going into the condensate, this is a terrible drawing of a condensate, but you kick a whole bunch of electrons out of valence and then they go into conduction, but then they themselves form this many-body excitonic wave function, which I wasn't able to draw using PowerPoint, sorry. But this should have some significant influence on the dipole moment. The slight issue is that whenever you have a condensate, it's not that you condense the entirety of this valence band. It's just some small fraction. But we think that we carefully estimate this small fraction. We believe this will have enough to be able to be seen in an experiment. Just here's a plot of our calculation. This is the full dipole moment. This is some probability weight factor. And what I plot is it's reduced in reduced units by this 2m delta for convenience. And you see some transition. So this would be the exotonic condensate with a lower polarization than the band insulator. And then once you get to the critical point, of course, they merge. So if you could, my understanding, and I don't know this, and I'm hoping to discuss with the appropriate people, is that via quantum capacitance, you could potentially measure some dipole moment. And if you took appropriate derivatives of this, maybe you could then see signatures of a quantum phase transition. And the final point in this messy slide is the spin and valley structure. So at the start, I said that spin singlet equals spin triplet. And this is basically a byproduct of us choosing a density-density type interaction, but which ignored exchange interactions. So we go ahead and compute exchange interactions, and it turns out that for the L equals 0, so the spin wave, so the S wave and the P wave excitons, the exchange interaction is identically 0, not just numerically close to 0. There's some selection rule that rules out this exchange interaction from having any influence. So singlet remains equal to triplet, remains degenerate with triplet. That's more just theoretical interest. But the valley degeneracy is already broken at the level of density-density interactions. And this is by this form factor, which I said just imagine is 1. And what's actually favored is the P equals 2K state. So this has an observable difference to the P equals 0 state, because if I look at the real space order parameter, it has some non-trivial modulation that's not exactly, some non-trivial modulation. And I don't know, maybe this could be measured with SDM, but I'm not sure, but it's interesting to me anyway. And I've raced through, so that I'm already at the end. Thank you.
Well, okay, thanks. I guess I was going to ask you a bit more about the experimental situation, or maybe you explained it, you showed a little bit, but maybe it's sort of summarizing where they are, what they would need to do, what are the prospects of testing it, you know.
So the question is how to test for this.
Yeah, partly that, and partly like what are the experiments that people are doing, and I assume that they've made the bilayer graphene with the 2 different voltages on the 2 sides.
Yes, right, exactly. So the experiment that is available, there's a science paper from maybe 2013 or something like this. They have bilayer graphene, but they have HBN encapsulation. So this is, and the gates are at 20 nanometers. But they probe and they're looking, let me look at this data. This is I've extracted their data, but they're in this, okay, unfortunately I plot in 2 delta because this is the way they do it. But they look in this regime, which is deep in the band insulator. So really they're exciting individual excitons. I'm not aware of any experiments that go down to or we'll go either to really large distances for the gates, or go down to the suspended bilayer graphene limit, which is epsilon r equals 1. So as far as I know, experiments haven't probed the appropriate regime to see condensation to prove us wrong yet.
Okay, thanks.
Thank you.
Could I ask a question? So the perturbation theory implies the presence of some small parameter. How its use is justified here?
Yeah, this is a good question. This is a very fair question. So you can see from here, basically, there's some, well, it's hard to see, but on the order of 30–40% change in energy, say delta B over delta naught. So in principle, we need to go beyond first order perturbation theory. But we truncated the perturbation theory there just because of numerical difficulty. So it's sort of, it's getting close to the limit of validity of first order expansion, but it's still okay.
Okay, thank you.
Thank you. Yeah, good question.
Hi, thanks for the talk. I do have a question about this sort of retardation effects. Do you have a sort of a physical interpretation as to why the retardation effect appears to enhance this Coulomb potential?
So, okay, the one thing I said, so the physical statement I made is basically that if excitons, so an electron and a hole, interact instantaneously, then they experience a weaker attraction than if they interact at two different times. Now, how I understand this is more at a theoretical level, in that you have this polarization operator. Okay, equation 10. And here I've done everything in imaginary frequency, in Euclidean frequency. But if I do this in real frequency, what's happening is that at some point at large real frequency, this denominator can actually go to 0. And so if it was an equivalent problem of, say, a Fermi surface, and you looked at dynamical screening on a Fermi surface, this is a plasmon pole. So what you're doing is, by inducing this large frequency response, in some sense, you're invoking a new quasi-particle, new bosonic quasi-particle in the system, which has some pole, which is a totally not intuitive way of saying it, but that's how I visualize it.
I see.
So it becomes, so you imagine it's more like a spin fluctuation exchange. You know, you can enhance attraction or interaction between two particles, or even phonon exchange. So say in normal BCS theory, you have some originally repulsive Coulomb interaction, but because you have some bosons in the system, phonons, you can, with the phonons, you go beyond this bosonic pole, and then it becomes attractive. Here, we're sort of on the other side, we have an attractive interaction to start with, and then you have these bosons which are approaching the pole in equation 10, basically the 0 of equation 10. So that's why I said as well that there is some physical meaning to anti-screening, but it basically becomes an effective boson exchange theory.
Okay, I see.
Thank you. That's a really good question, but I'm sorry I didn't have a more physical way of explaining that. I have to think about that. Thanks.
But maybe I can say also,
Yeah,
can I add if you, so it's just, there is a usual Coulomb attraction, and plasmon exchange helps Coulomb attractions. That's it. I would, and this is what you actually said, Harley.
Yeah.
This is a simple physical picture. Plasmon exchange.
Yeah.
Okay, thank you.
Thanks, Oleg. Alex has a hand up.
Just a question about the screening. So for the screening, you're using both the conduction and valence bands.
Yes.
And is the screening depending on the exciton density? Because the number of electrons and holes you've stolen from the bands increases as you condense more?
Yeah, so the trick is that basically everything I've presented where I do this rigorous calculation, say with equation 10, I'm strictly in the band insulator regime. So so in essence, these are like virtual excitons of kind of what are appearing out of this polarization operator. But you're absolutely right. As soon as I go into the condensate phase, I need to take into account the back action of the condensate on the whole, on this Coulomb interaction. And this is a very interesting problem. But basically, once we get to the condensate, we say, oh, well, two-body techniques are out the window. We just wanted to pin down some phenomenological properties. But certainly this is something you absolutely have to take into account. And what would happen just naively is that you start with a band insulator and you enter the condensate. This actually pushes the bands apart even further. So you gap out the bands even more. So just at a qualitative level, the larger you gap of your insulator, the less screening there is. So just if even without the dynamics of the exotonic condensate, if it was an exotonic autoparameter, you can kind of convince yourself that actually it would further enhance the Coulomb interaction. Up to some point, of course, this was uncontrolled. But yeah.
So then you would see that easily in transport. You would suddenly see your resistance shoot up because your band gap has been enhanced by the exotonic condensate, which is neutral.
I mean, maybe it's a band insulator to begin with. So, yeah, I'm not sure if there's suggestions for experiment. Then, yeah.
Alex, what do you mean? You mean this is insulator? You say activated, temperature activated?
Yeah.
Interesting point.
Yeah, that'd be a great way to measure if you can measure this band gap.
Temperature activated.
Well, I mean, pardon me. You could thermally excite the band gap, but also as you vary D, what you'll find is that your band gap is not opening linearly with D, right? Because of the exotonic condensation. As soon as the exotonic condensation starts, you push your bands further apart.
Mm-hmm.
So I'm surprised that this hasn't already been seen in experiments, because Bilayer graphing is quite heavily studied.
But there's 2 points to that. Is first, how do they measure that band gap? I mean, if they are moving the chemical potential around, then you're also killing the exciton physics. And the other point is that I think that people have been pretty restricted to D equals 20 nanometers. Again, I'm basing that on one experiment.
But Alex, maybe also I can add what we found that just, and this probably explains when you have separated two different graphene layers. Any metallic screening is killing to the effect. A little bit of metallic screening immediately kills everything. Or kills, I mean, critical temperature becomes absolutely close to zero.
Yeah.
Right. And here, playing with the gap, we can optimize interplay between screening and condensation. And this is essential handle.
So if I take this approach and I start to now create indirect excitons.
You mean between valleys?
Well,
or
yeah,
between...
or if I, no, if I, and maybe we can talk afterwards. I'm just trying to relate it to experiments I know about.
Okay, maybe maybe we can talk. Mm-hmm. But here, critical temperature is enormous, and we are very confident in this.
Could I ask another question?
Please, please.
So you use random phase approximation for the screening.
Yes.
Here, it usually assumes that RS is small, but in your case, RS is very large. Am I correct? If you introduce this standards Wigner-Zeitz radius parameter.
Yeah. So I guess that's the classical way of justifying RPA. But the other way is obviously by 1 on n corrections, as you know.
Yeah,
So
it's
we have
1 over 4.
1 over 4 is 0, obviously. So RPA is justified. Yeah, no, that's a good point. I mean, we can, of course, it would be interesting to look at vertex corrections or whatever other corrections there are. But we have this, yeah, 1 over 4 at the moment, suppression.
Yeah. No, but again, it's this correction, frequency dependent correction, is ultraviolet logarithmically divergent. Therefore, it's getting less and less. All vertex correction are getting less and less important.
Mhm.
I think that it's well beyond reasonable doubts. It's correct. This is behind the factor 1 over 4.
Mm-hmm.
Okay, thank you.
Hello, I like nice talk and great work there. I had a quick question. Is the G factor you mentioned in the puzzling Zeeman splitting, right? Is it isotropic in B? Because based on what I'm doing, I guess the G factor has to be announced in like the perpendicular magnetic field direction to the plane compared to in plane. So
Okay, so sorry. Yeah.
do you have any idea about it? Like,
So you say, what's the G? So this is for outer plane magnetic field.
yes.
And if I put it in plane, then the G factor will be totally different.
Yeah.
Because here, this G factor is basically this S wave. Okay, for S wave is what we condense. Is the difference between this valley S waves forming in valley plus versus valley minus. And you're able to access the orbital dynamics of this valley when you have an external, when you have a perpendicular to plane. If you just put it in plane, then you can only access the Zeeman splitting due to spin. And so there's G factor about 2. So you got 20 versus 2. Yeah.
Yes,
so
that's what I've observed as well in the
excellent.
work I'm doing. Like,
Yeah.
sort of. Though it's not like 19, but it's still comparatively larger, like 5 or 6 times larger than normal Zeeman splitting.
Yeah, yeah. Well, there's a trick. Maybe the G factor is 4 because of it's an S.
It depends on the gamma 4 factor, which is the electron hole asymmetry you're introducing in the system that you just mentioned. True. So I agree with that. No problem. I just wanted to make sure.
Yeah, sure thing.
Thank you.
Thanks.
Okay, I think we've had questions, and I guess Harley is available. And if you want to reach out to him afterwards, if a question comes to mind later. Anyway, thanks so much. It was really interesting, and thanks for you obviously made a real sincere effort to make it understandable even to the non-experts, and really appreciate it.
Okay, thank you for saying that.
Okay.
Yeah.
Okay, great. No, thanks a lot. Okay.
Thanks everyone for tuning in. I really appreciate that. Thank you.
Okay, great. Have a great day.
Okay.